For this one, we have a diagram showing us that these two triangles are similar. They gave us the order of similarity here. We're going to have to pay close attention to that as we do this problem. So based on the diagram, we want to know the measure of angle K. That's our ultimate goal. So I could figure out the measure of angle K if it's either equal to S, or if I can at least figure out J, then I could subtract that 90 from 180 to get K. So the only angle that they gave us other than these 90-degree ones, which we know U and L are going to match up, is this 60-degree angle. What angle is S equivalent to over on this triangle? To figure that out with certainty, other than just trying to eyeball it here, if we look at the order that things appear in the similarity statement, S is the first letter in its part of the statement. That means it's going to correspond with J, which is also the first letter in its part of the statement. So J and S are the same angle. So I'm going to write a little 60 in here just to remind myself that J is 60 degrees. And now to get K, I just have to add 90 and 60 and subtract that from 180, and that'll get me my K value. 90 plus 60 is 150. That leaves 30 degrees left over for angle K, which is choice B. On this problem, we are being asked to order these rates from least to greatest. The catch here is that these are all in different units, both in terms of distance, we have miles, feet, and yards, and also in terms of time, minutes, seconds, and hours. So I have a hunch these are all kind of pretty close in actual value if you were to convert them into the same units, so it's not obvious which one is biggest and smallest. My trick on this one, and there's a lot of ways you could go, I'm going to just convert everything into feet per second. And the reason I'm choosing feet is because that's the smallest unit of measurement out of all of these, and seconds is also the smallest time unit out of all of them. So I figure it'll probably be easiest to go in that direction. So let me start by converting this 1 mile per minute into feet per second. First thing I'm going to do is convert miles into feet. I know there are 5,280 feet in a mile, and that's actually on your reference sheet that you can look up. So I'm going to write 5,280 feet over 1 mile, and this is going, and I'm going to multiply by this little conversion factor, and this conveniently cancels out the miles. So now I'm going to have feet per minute, but I want feet per second. So next I'm going to multiply by, let's see here, I want to get rid of minutes, so I'm going to have 1 minute for 60 seconds in my next fraction. Now my minutes are canceling out, and I've got 5,280 feet over 60 seconds. However, if I'm going to be able to compare that to this 100 feet per second, I want to reduce this and divide it. So let me divide that on my calculator. So 5,280 divided by 60 comes out to exactly 88 feet per second. So far, this is the smallest quantity out of the ones that I can compare. Let me do the yards per hour next. So I'm going to replace yards with feet, just like I did with miles. But now, every yard is equivalent to 3 feet. So I'm going to write times 3 feet over 1 yard. Yards cancel out. And now I want to convert hours eventually into seconds. Maybe you don't know exactly how many seconds are in an hour. That's okay. We can convert to minutes first. We know that there are 1 hour is going to be 60 minutes, so hours cancel. And now if we want to convert minutes into seconds, again, from up here, we know that 1 minute equals 60 seconds. So we can now cancel out the minutes. Multiplying everything through here, I'm going to have 300,000 yards up top and 3,600 seconds down below, or 300,000 feet, I should say, because the yards have been canceled. Only the feet is not crossed off there. And then the seconds are below. So I'm going to run this on the calculator as well, because I have no idea what that is. So 300,000 divided by 3,600 comes out to roughly 83.3 feet per second. So now ordering these from least to greatest, this 83.3 is less than the 88 and the 100 feet per second that I had. So that means 100,000 yards per hour is the smallest quantity. And next up is the 88. That came from the 1 mile per minute. So that's This is less than that, and that is less than what they gave us in the beginning. The 100 feet per second ends up being the greatest. For this problem, we've got a bag with 21 red marbles and 4 blue ones, all the same size and shape. 2 are going to be picked out of the bag randomly, and the first marble will not be replaced in the bag before drawing the second. So here's the problem. Given that the first marble selected is blue, and therefore not returned to the bag, what is the probability the second marble selected will also be blue? So we're asking for a single probability, but we're asking for the probability of blue given that blue has already happened and not been replaced. So let me just look first at my first probability, the probability of drawing that first blue marble. So there were overall 21 plus 4 marbles in the bag, so that was the denominator on that probability, and it looks like 4 of those were blue. So 4 out of 25 was the first blue. Now, the important piece here is that since we're not replacing any of the blue marbles, that means that there is 1 less marble overall. So instead of 25, we're going to have 24, and there's also going to be 1 less blue marble specifically. So this 4 will now be a 3. So then we'll have to write 24 in the denominator, 3 in the numerator. This is the probability of our second blue given that the first has already happened. And this matches up with answer choice A. We could reduce it, but they already gave us the answer. For this one, we have a ball being dropped from the top of a ladder, bouncing. And here's a function that models how high it bounces after the end bounces, how high the bounce is. So we want to know basically in this formula what the 96 represents. So in general, these exponential models, the a, b to the n sort of deal, in these, the a, the number that's being multiplied but doesn't have an exponent on it, that's your initial value. Because if you plug in 0 for the exponent, you're going to have something to the 0, which is just 1, and all you're going to be left with is this initial a value. So that means that this 96, since h represents height, 96 is the initial height of the ball at time 0. In other words, before it actually gets dropped. So that would be then choice B. For this fun problem, we have a circle with a diameter of 10, gets cut up into 24 equal pieces, and then they separate those kind of like pizza slices, rearrange them, and put them back together in the shape of, this looks to be roughly like a parallelogram sort of thing. I've actually seen this before. This is actually the proof of the area formula of a circle, but that's not what they're asking about here. What they want to know is this x length, what's this closest to? So we kind of have to trace this back where this came from. So x is this distance over here, and this distance is this outside. This is like the outside of the circle. This is half of the circle right here, so half the way around. So we can then say that this distance is essentially half of the circumference of the circle, 1/2 times c. Now, in order to actually get some numbers we can use, it'll be helpful if we think of circumference as 2 pi r. 2 pi times the radius, or pi times diameter is fine too. So I use 2 pi r, but pi times diameter also works. That means the 1/2 and the 2 are canceling out, so my x value is really just whatever pi times the radius is. In this case, the radius is half of 10, so 5. So whatever pi times 5 is, and pi is roughly 3.14. If I multiply that by 5, just looking at these answer choices, that's going to be closest to 16. So that's the answer choice we're going to pick, B. For the next few problems, we're going to use this chart here, this histogram. We have juniors and seniors at a high school being surveyed about whether they ever had a summer job. Here's the breakdown. So based on the graph, this is part A, we want the total number of students who were surveyed. Well, each of these bars here represents a different group of students. We have the juniors who had a summer job and didn't, and the seniors who had a summer job and didn't. So we just need to figure out what all these are numerically and add them together. So for the first bar here, this is 100. That's juniors with summer jobs. The no summer job juniors were 200, so we'll add that in. Over here we had 100, let's see, this is 125. These grid lines are going by 25s. So that's the seniors who had a summer job, and the ones who didn't was a little bit more at 150. Adding these all together, this is, let's see, 100, 300, 425, 575 all together, but you could confirm that on the calculator. For this part of the problem, we want the probability that a randomly selected student had a summer job and is a junior, and show or explain how we got the answer. So in general, we're trying to figure out, for our numerator and denominator, we want the summer job juniors in the numerator, and we're going to be dividing that by the total students. They said a randomly selected student, and they didn't say anything else about what that student had to be until they get to this part here. So that's going to be summer job juniors over total students is how we're looking at this. The total students we already found, that was 575. The summer job juniors, that's this box right here, that was 100. And if you want, you could reduce this by 25. So that would be 4 over, well, let's see here, 600 divided by 25. That would be, how many quarters would that be? $6, that would be 24 quarters. So 1 quarter less would be 23. So then 4 over 23 if you wanted to reduce it. For the next part of the problem, this wording is kind of tricky here. They want the probability that a randomly selected student had a summer job given that the student is a junior. So this is some key wording here. If we're given that the student is a junior, then we're not considering all 575 students. We're only considering the juniors. So when we do this, we're still doing summer job juniors for our numerator, but now we have to divide that by just the total number of juniors, because we're not allowed to even think about the seniors. They don't even exist for this problem. So for total juniors, that would be 100 plus 200, total of 300 juniors. And the summer job ones, again, were 100. We've used that a couple times now. And you could reduce that to 1/3 if you wanted. For the last part of this problem, based on the graph, are juniors or seniors more likely to have had a summer job? Here's the key, though. Explain your answer using conditional probabilities. So if you just look at the graph, the seniors are a lot more evenly balanced between the summer job and the no summer job. It looks like a higher proportion of the seniors had summer jobs than didn't, versus the juniors. So just eyeballing this, it looks like the seniors ought to win this contest here, but they said using conditional probabilities. So we have to show them the numbers. So the first one we're doing is we're trying to figure out the probability that a student had a job given that they are a junior. That's the condition there. The condition is that they're a junior already. Now the good news is we already found this in part C. This was 1/3, 100 over 300. So now we actually just need to find the probability that a student had a job given that they are a senior. So the total number of seniors was going to be 125 plus 150, so 275. And the seniors that had a summer job was 125. Reducing this so I can more easily compare it to 1/3, this is going to be 5 over, let's see here, 11, I think. 11 quarters to get $2.75. And if you're not sure which one of these is bigger, you can always use a calculator in this section to compare them. So here I am on the calculator. 1/3, we probably know that's 0.3333, but if not, there's the calculator. And 5 over 11 gives us a higher decimal, 0.45 and some change. So 5 over 11, we've just proved it there, is bigger than 1/3, which means that the seniors have a higher probability, higher conditional probability of having had a summer job. On this problem, we are given this triangle, and we're told this is going to be dilated by a scale factor of 2.5 with respect to the origin. We want to graph the image after the dilation of this triangle. So basically what we're doing with this 2.5 scale factor is we're multiplying both the x and y values each by 2.5. So I think the safest way to do this problem is to actually write down the numerical points that are in this triangle, do this multiplication, and then regraph what we've got. If we were just doing a single point, I might think about eyeballing it, but I want to be careful since we're doing a bunch of these. So one point I see on here is -2, 2 right there. And if I multiply that by 2.5, -2 times that becomes -5, which you could do on the calculator if you want. And then 2 times that becomes +5. Next, we've got the point 2, 0. I'm going to do all the points first, and then I'll graph everything at once here. So multiplying that by 2.5, 2 times 2.5 is 5. 0 times anything is 0. And then finally, we have this point down here, -2, -4. -2 times 2.5 we already saw up here was -5. -4 times 2.5 is -10. Let me go ahead and graph all these now. So we have -5, 5. So that's right up here. And then we had 5, 0. That's going to be over here. And then finally, -5, -10. So we're going left 5, down 10 right there. And connect the dots. There is our dilated triangle. On this problem, we have a restaurant serving iced tea in small and large glasses. We are told that 1 small glass and 2 large has 48 fluid ounces of tea, whereas 2 small and 3 large gives you 76 fluid ounces. We basically want to know the number of fluid ounces in 1 large glass. So this is a systems of equations type of problem. We have 2 different sets of information about really the same stuff. So I'm going to set up a couple equations. I'm going to let S represent the number of ounces in a small glass, and L will be the number of ounces in a large glass. So based off this first sentence here, we can say that 1S plus 2L equals 48 fluid ounces. And using the same kind of setup for the second statement, we have 2S plus 3L equals 76. And now to solve this, I can choose between substitution and elimination. Really dealer's choice on this one. They're both about the same, but I'm leaning slightly towards elimination because I want to do something to get rid of I'd like to get rid of the S right away. Actually, either method would get rid of S right away. You could subtract 2L and then substitute 48 minus 2L for the S over here, and then you would just have L's. But what I chose to do is I actually multiplied this equation here by -2, because doing so is going to give me a -2S right here that on the next step is going to cancel out with this positive 2S. There are other ways to do it, but this is how I went. And then we have -2 times 2L, that's -4L. -2 times 48, that's going to be -96. And then adding these two equations together, my S's cancel. I've got 3 plus -4 is -1L. And then 76 plus -96 is -20. Nice kind of round number there. Then just dividing both sides by -1, we have L equals 20. So that's telling us there are 20 ounces in 1 large glass of iced tea, which sounds realistic. So that's going to be choice C. For this one, we have a circle with an inscribed quadrilateral going on, and these angles have some expressions attached to them. We want to figure out basically the measure of this angle V. So clearly, in order to get V, you're probably going to have to solve somehow for X. Now, the key on this one is that it's not just any shape, it's a quadrilateral. And these two angles that they gave us information for, they both are inscribed angles that intersect the same spots here. So between these two angles, they actually go with arcs that collectively make up the entire circle. V covers this side of the circle, and angle T covers the rest of the circle that V wasn't already covering. So if the inscribed arcs are each half of the, or if the inscribed angles, I should say, are each half of the arc that they intersect, and they're intersecting the whole circle, that means together these angles must be half of 360, or 180. So the way I'm going to kind of unlock this thing and solve it is I'm going to do 5x minus 1, this angle here, plus my other angle, 3x plus 5. Again, those both have to add up to 180. And then if I just solve for x, let me combine some like terms. So 5x and 3x is 8x. Negative 1 and 5 is 4. Subtracting 4, that's 176. And dividing 8 into 176, well, 8 goes into 160 20 times. That's 16 more than 160, so that's going to be 22, which you could do on the calculator if you want. So we have 22 for x. Now that's not any of the answers, and it shouldn't be, because that's not the value of angle V. Angle V, you have to do 3 times 22 plus 5. You actually have to plug x in there. So this is going to be 66 plus 5, which is going to be 71 degrees. Choice B. On this problem, we have a barber taking between 20 to 30 minutes to give a customer a haircut, and the barber is going to give haircuts for 8 hours today and has already spent 96 minutes cutting hair. Not that anyone's really keeping track. We want a reasonable estimate for the number of additional haircuts the barber can give on top of what's already happened, which we have no idea how many it actually was. And based off of that, we're going to call each of these things reasonable or unreasonable for a number of haircuts. So here's the strategy I think we could use on this one. First, it would be nice to know, based off of this 96 minutes and the hours we're working, how many minutes of haircutting still remain in the day. Once we figure out how many minutes are left, we can divide that by 20 and 30, and that'll give us kind of an upper bound and a lower bound on how many haircuts we can reasonably give. So first off, the number of minutes left, we're going to have the number of minutes in 8 hours, 8 times 60, minus the 96 minutes we've already used. Let me just put that in the calculator to be careful here. So 8 times 60 minus 96 comes out to 384. So now to figure out the minimum time, we assume that, or I should say the minimum number of haircuts, we should assume that we'll take 30 minutes on every single haircut, and we'll see what 384 divided by 30 is. So the minimum haircuts then, going back to the calculator, 384 divided by 30 comes out to 12.8. So let's just round that off to be reasonable to 13 haircuts. Now the maximum haircuts, that'll be if you take your remaining time and somehow you just blaze through each of these with only 20 minutes spent per haircut. So this is assuming the best case scenario, at least in terms of number of haircuts delivered. And let's see what that comes out to. So 384 divided by 20, that's 19-ish. So we'll call it 19. So that means that reasonable would be somewhere between 13 and 19 haircuts. Now let's look at each of these options here. 16 haircuts, is that reasonable? Well, that's squarely between 13 and 19, so I would say that's definitely reasonable. And then now 24 haircuts, well, that's 5 haircuts over kind of our maximum number that we could pump out here, doing only 20 minutes a haircut. So 24 doesn't sound reasonable based off of that. And if 24 is too many haircuts, well, then 32 is even more unreasonable. So this X should go like somewhere over here, I guess. And there we have it for reasonableness. On this problem, I'm actually going to use this pentagon graphed on the coordinate plane for a couple problems. The first part is we're just asking for the perimeter in units, whatever that means, of this pentagon. So we have to essentially figure out how long each of the sides is and add all of them together. I'm going to start with the low-hanging fruit. This horizontal line seems pretty easy. That's just 3. And then this vertical piece here is clearly just 4 if we count the grid lines on that. Now we get to the harder ones here, these slanted lines. Now these are basically just, you can think of these as each of the hypotenuse on a right triangle. So if we have a right triangle with one side is 3 and the other is 4, to find this length we can just do the square root of 4 squared plus 3 squared, or vice versa. Basically a squared plus b squared, and then square rooting that piece of it to find the c value. We'll figure that out in a sec, moving ahead, though, let's just set the rest of these up while we're thinking Pythagorean. This next side here is also a hypotenuse. This triangle has a base of 3 and a height of 4. So it's actually the same dimensions as the other triangle over here. So I'll just use square root of 3 squared plus 4 squared. Again, it doesn't really matter what order those go in. And then finally, this side, we have 3 and 4 as the two sides of that invisible triangle. So again, square root of 3 squared plus 4 squared, or vice versa. Now, you could add these together. This is 16 plus 9 in here, which is 25, and the square root is 5. Or you might just recognize that this is a 3, 4, 5 triangle. That's cool, too. So at the end of the day, each of these square roots, they're the same thing. These are all 5s. So we have 3 plus 4 plus 5 plus 5 plus 5. Let's see here. This is 7, 12, plus another 10 gives us 22 units. Again, whatever that means. That's going to be choice B. For this second part of the problem, we want to find the area in square units of the pentagon. So because there isn't really like a hard and fast pentagon area formula, we're actually going to have to chop this into shapes that we already know how to find the area of. So let me just start by finding the different sides of this pentagon again, or at least labeling them, and that'll give me a starting point. So we knew that this side, and this side, those were all 5s. And now if I'm splitting things up, well, actually, let me do these other ones here. So this is a 3 up here, we said. This was 4. And now if we're splitting this up, I think a good place to split this up, there's lots of options. I would split it up right here, though, because I know here, if we look at this, this is the hypotenuse of a right triangle with a 3 and a 4, so this is a 5 for that side. That gives us two shapes here. This shape here is actually a square. It's just a rotated square, but it is a square. All 4 sides are the same, and we haven't really proven it, but these all look like they're going to be right angles here. And now this up here is a triangle. So for my overall area, I need the area of a square, s squared, plus the area of a triangle, 1/2 base times height. For my square area, I'm squaring 5. That's the side of the square. And 1/2 base times height, that's 1/2 3 times 4, or 4 times 3. It doesn't really matter what order those go in. So this is going to be 25 plus, let's see, this is half of 12, so half of 12 is 6. And then adding those together, we have 31, and just to make them happy, we will write units squared on that. On this problem, we've got a histogram showing the number of people in a city by age group, and these are all going by thousands, but since they eventually want the fraction of the total population that's between the ages of 20 to 59, since they're just looking for a fraction, we don't really have to worry about the fact that these are all expressed in thousands, because that'll all get canceled out anyway when we write our final fraction. So, first task, let's figure out how many people are in the city altogether. So our grand total, just adding up these different categories, in the 0 to 19, we've got 11 people, plus another 18, 17, this is 15, and this one right here is 4. Adding that all together, let's see, this is going to be 29, 46, 61, 65 if we add all that. And we also need to know the people who are specifically just 20 to 59. So in the 20 to 59 category, first we've got this 20 to 39 box here, and again there's 18 people there. And we also have the 40 to 59, 17 people there. So 18 and 17 gives us 35. So the final fraction then, we've got 35 out of 65, which we could reduce if we wanted to, but I see that it's already one of the answer choices right here, and there's no other reduced answer choices, so we're going to go with choice D. For this multi-part problem, we have a vase in the shape of a right circular cylinder with a diameter of 22 centimeters. First question, we want to know the area in square centimeters of the base of the vase. Since it is a circular cylinder, that means the base is a circle with an area of pi r squared. So we've got pi times half the diameter, so 11 squared. And they didn't actually specify that we had to round this off, so the most exact answer would be 121 pi, and this would be in centimeters squared. But if we wanted to round it off to an exact value, which we might need to do later anyway, let's plug that in the calculator. And then 121 pi in the calculator comes out to 380.13, and you could use 3.14 if you don't have a pi button. And again, that's square centimeters. For part B of this question, we're filling the vase with water to a depth of 10 centimeters, and we want to know the volume of that water. So we're talking about the volume of a circular cylinder. The water is going to take on the shape of the container. So we're talking about a cylinder. That's going to be pi r squared h for the volume. So in this case, we've got pi times, again, 11 squared, because that's still the radius, times the height now of 10. So this is what we're either doing out on paper, plugging into our calculator. This was 121 pi times 10. So this is 1,210 pi cubic centimeters. Or again, we could convert that into a decimal on the calculator. So as a decimal, that's coming out to 3,801.33 cubic centimeters. For the next part of this problem, we're putting a solid sphere with a diameter of 12 centimeters in the vase, so at least the diameter is less than the container itself. We want the volume of the sphere. So for that, we need our sphere volume formula, which you can look up on the formula sheet. That's going to be 4/3 pi r cubed. And then we have to plug in our radius. Now, you got to be careful plugging this in here, because we're talking about the radius of the sphere, not of the cylinder. So we're going to use 6, half the diameter of the sphere, for r. And plugging that in, I'm not even going to bother getting an exact answer with pi. Let me just go straight to the calculator for this. So plugging all that in, for 4/3, I'm going to use parentheses 4 divided by 3. I've got my pi in there. Again, you can use 3.14 for that. And I've got 6 to the 3rd power, which is 216 if you have trouble finding the exponent button. Pressing enter, that comes out to 904.78 cubic centimeters. For this last part of the problem, we've got a sphere now that we put in there in part C, sinking to the bottom of the vase, and as a result, our water level rises. But this is important here, the water does not overflow, because that would be a very different problem if it did. So we want the number of centimeters that the water level rises when the sphere sinks to the bottom. So we need to get a strategy to kind of figure out how we're going to do this. In general, I'm looking for the change in the height. So I need to figure out kind of the new height based off of the new volume. That's really going to be my strategy here. So I'm going to figure out the new volume by combining the volume that was of the water before we put the sphere in, and also combining the volume of the sphere itself that we figured out in part C. Once I have that new volume, I'm going to then work backwards to find the new height of the water. And once I know that, I can subtract the old height of the water to find how much the height actually changed. So there's really 3 steps here. So first, let's find our new volume. So from part B, the volume of the water that was in there, the 10 centimeters of water, that was 3,801.33 cubic centimeters. And then you might recall from part C, the volume of our sphere we found was 904.78 cubic centimeters. Adding those two together on the calculator now, let's see what we get for the new volume of the stuff inside the cylinder. So adding that up, we end up with 4,706.11. I'm just going to keep it out to 2 decimals here because you need to be at least 1 decimal of accuracy. And now we're going to work backwards. So this is the volume of the stuff in the cylinder. I'm going to set this equal to pi r squared h, my general formula for the volume of a cylinder. And again, I'm going to work backwards to find the h value. Now I know the r value here, but I'm gonna first solve for h just so I don't have to plug anything in right away. So my h is going to be this new volume divided by pi r squared. Now, the radius we're talking about is the radius of the circular cylinder, which is also the radius of the water level. So we've got 11 for that. We'll have pi times 11 squared. And I'm going to run that on my calculator now. Here's what this looks like on my calculator. I've got 4,706.11 divided by, and notice I'm using a parentheses around the pi times 11 squared. If I don't do that, then I'll accidentally be just dividing by pi and then multiplying whatever that result is by 11 squared, which is going to give me something I'm not expecting or wanting. So I use that parentheses down there, and this all comes out to about 12.38. 12.4 we'll round it off to. Now, we're not done with the problem because they asked what's the number of centimeters the water level rises. So to get the change in the water level, I need to do 12.4 minus the original height, which was 10. And then that's going to be, I don't need a calculator for that. That's going to be 2.4 centimeters that our water is rising. For this two-part problem, we have a student with an after-school job, and here's the function modeling how much money the student has working H hours a week. Now, we're told that the student can work a maximum of 20 hours a week. I know some businesses have gotten in trouble for having students work more than certain legally required maximums of hours, so this is a very feasible real-life situation. Based off of this, we want to know the domain of the function. That's the first part of this question. So the domain is all the acceptable inputs, and the inputs in this case are the number of hours that our student can work. So we have to figure out how low can we go, how high can we go. So for how low can we go, the student can't work less than 0 hours. That's just physically impossible. I'm not even sure what that would look like. And because of this legal maximum here, we can't work more than 20 hours either. So then our domain would just be all the H values between 0 and 20 hours, including those. So that would be choice B. For this second part of the problem, they want to know the range of the function. So in terms of outputs, in terms of money that we can earn, how high can we go? So there's two key pieces to figuring this out. First, we need to know all the acceptable inputs because those are going to determine the outputs. We saw from part A that our domain, our inputs, ranged from 0 hours to 20 hours. So we can get those values and all the values in between. Now we can't assume that 0 and 20 are also going to give us kind of the outer limits of our range. In order for that to be true, we would need a function that is either increasing or decreasing consistently all the way. And now if we think about money here, earning money, this is a function that is only going up. We're talking about how much money the student has earned. That's only going to increase as time goes on. So this is an increasing function, which means to find the lowest and highest values, we really do need to just plug in the starting and ending H values. So our M of H is going to be between M of 0 then and M of 20. Now, M of 0, if our student works 0 hours, predictably they get $0. So that would be 0. And for 20 hours, we're just doing 12.5 times 20. 2 times 12.5 would be 25, so 20 times that is 500, but you could use the calculator. So we are clustered then between 0 and $250 for the range of this function. On this problem, we're told that triangle EFG is similar to triangle JKL. They've given us the measures of angles E and K, and based off of that, they want the measure of angle F. Now, what makes this a little challenging is they didn't give us a picture, so we have to supply our own, and we want to draw our pictures so that our angles match up with each other. We want E to match up with J, F should match up with K, and G should match up with L because that's the order that these were written in. So here is triangle EFG. I'm going to start in the lower left and just kind of work my way around counterclockwise. And for triangle JKL, I've got JKL going on here. Let me also, now that I've drawn these, fill in my angles. So we have angle E right here is 32 degrees, and angle K, that's over here, is 49 degrees. And they want the measure of angle F. Now the key here is, since these are similar triangles, I mean, I know they look congruent. I didn't bother drawing one a different size. They're at least similar. That means that all the angles are the same, the corresponding angles. So angle F should match up with angle K, which means that the measure of angle F is the measure of angle K, which is going to be 49 degrees. So that's choice B. And then this 32 degrees just didn't get used at all. On this problem, free response problem, we have a marketing company surveying random customers from 2 different age groups about favorite types of juice, and they gave us these results in this 2-way table here. Based off this, we want the percentage of customers surveyed who chose apple juice as their favorite type of juice. So if we want the percentage, we need to figure out, what this is out of, and then how many people are in this group that we're choosing to look at here. So they just said percentage of customers. They didn't specify an age group or anything else. So we're just talking about the total customers for the denominator of our fraction when we turn around to divide some things. Total customers is 500 here. And then we just want to know how many chose apple juice. So this would be the total that chose apple juice, not just for a specific age group, but everybody who chose apple juice, which is this 220. And then we just have to divide that on the calculator if you want. Let me go ahead and do that. So doing that division, I end up with 0.44, which means I've got 44% as the total number of people who prefer apple juice. And all the other things in this table, again, we didn't really use them a whole lot. They were just sort of there as filler and distractors. For this problem, we're talking about a construction. We've got angle Y, and then we drew an arc with a compass from point Y through the sides of the angle to create points X and Z. So X and Z, they're going to be the same distance from Y. And then, let's see here, we drew some arcs from X and Z, and where those arcs intersected, that gave us point P. And then we drew a ray through points Y and P. So we want to, based on this construction, we want to figure out which of these could be true. Basically, what you've drawn here in doing this, since all these different distances are the same because you were using a compass with the same settings, you've drawn an angle bisector. Because this is an angle bisector, and if you didn't know this off the top of your head, you could kind of just look at this diagram, which should be drawn to scale. I mean, that's the whole point of doing these constructions, is you get things that are as accurate as they can be. These angles do look to be the same, so this does look like an angle bisector. Since this is an angle bisector, that means that angle, let's see here, what is it, PYX, this angle here, and angle PYZ, this angle here, these angles are the same. So this is a true statement in choice A. Choice B, we're saying XYZ, that's this whole angle, what used to be just angle Y. They're saying that that is half of PYZ. Well, PYZ is like half of XYZ. So this relationship here is actually backwards. We should say that angle XYZ is 2 times the measure of angle PYZ. So that is a false statement, and you could choose that and move on with your life. But if you want to look at these other choices, here they're saying that YP is an angle bisector. We said that earlier. That was kind of the whole point of this construction. And then we have point P in choice D. Point P equidistant from X and Z. They're saying this point is the same distance from these. And even if you don't know a whole lot about constructions, just kind of eyeballing it, this looks to be the case, and it is actually true because these arcs intersected when you used compass settings that were the same, and also the fact that X and Y were the same distance from a point that was further back. So we're getting the same distances all the way through here. So this is also a true statement. Even if you didn't know anything about constructions, though, this second statement, if you can read angles and figuring out which angles they're talking about, this one is just blatantly false. So we're going to choose choice B. For the next 2 problems, we're going to be using this diagram where we have a circle with a radius of 6 inches, and we've also got this sector in the circle carved out by a 120-degree central angle. First question, multiple choice. We want to know what's closest to the area in square inches of this shaded sector here. So in order to find that, it would first be helpful to know the area of the entire circle. So let me use pi r squared for that. That's pi times 6 squared, which I could round off to a decimal because all the answer choices are decimals, but I'm going to hold off on doing that. I'm just going to call this 36 pi for now. I can always be more decimally later on if I want to. Now, what I'm going to do with this area, I'm going to set up a proportion. And to do that, to help me kind of do a little algebra here, I'm going to label the area of this sector as A sub s, just so I can refer to it easily. So I know that the area of this sector and the area of the whole circle are in the same proportion that this angle is with the angles in the whole circle. So I can set up a ratio with that. I can say that the area of the sector divided by the area of the whole circle is going to give me the same ratio as 120 degrees over the degrees in the whole circle, 360 degrees. And now I can cross multiply to solve this, but before I do that, just to make my life a little easier, I'm just going to quickly reduce 120 over 360 to 1/3. That's an easy one to do. Now let me cross multiply. So I've got 3 times A sub s equals 36 pi times 1, so 36 pi. Dividing by 3, I've got the area is going to equal 12 pi. And if this were a free response, I could probably leave it like this, but since I need to match it with an answer choice, let me plug that in the calculator. So 12 times pi, or 12 times 3.14 if you don't have a pi button on the calculator, that's giving me 37.7, and that's square inches, so that's going to be choice D. For the second problem part, they're asking about the length of arc XY. So this is kind of a distance equivalent to the area problem we did in part A, only this time one other difference is that there's no multiple choice to choose from, so you actually need to kind of show your work and justify your answer. We're going to proceed just like we did on the last part though, and we're going to find the whole here. This is kind of a part over whole equals part over whole relationship. We're going to find the whole distance around the circle, also known as the circumference, 2 pi r. And we're going to use that in a ratio to figure out just this piece of the circumference. So 2 pi r, that's 2 pi times 6, so 12 pi. And then setting up a ratio here, we've got the distance from x to y, the arc there, the arc length, over the total circumference, 12 pi. That's going to be proportional, again, to the 120 over 360 angles, just like we did in part A. And just like we did in part A, this is 1/3. Cross multiplying now, 3 times measure of xy is going to equal 12 pi times 1, so 12 pi. So then the measure of arc xy, we're going to divide by 3 on both sides. That's going to be 4 pi. And I could just write inches after that. Well, actually, no. They said, what is the length to the nearest tenth of an inch? So they are actually calling me out here to actually get a decimal. So let me do that. So on my calculator, 4 pi, or 4 times 3.14, that's coming out to 12.6 if I round that off. And that'll be in inches, so there we are. On this problem, we're given 3 different situations, and we need to figure out in each of these situations whether we should model it with a linear or exponential function. So just a quick rundown of the main differences between these that'll help us choose. Linear functions, we're basically adding the same number each time, and there's a constant slope. With an exponential function, you're multiplying by the same number each time, so you're not going to have a constant slope. You're going to be increasing at an increasing kind of rate if it's a growth exponential function. So looking at our situations now, as 5-pound bricks are added to a cart, the total weight increases. The key here is we're adding these bricks to the cart, so that's addition, not multiplication, which means this should be a linear function. In the next one, number of people registered on a website doubles every month. Doubling right here, that means we're multiplying, so that's an exponential sort of scenario. And then finally, this last one, the total distance traveled by a turtle walking at a constant speed increases over time. And now the key here is they said we're walking at a constant speed. So the distance, we're just adding the same amount to the distance every second or minute or whatever. So this is going to be a linear function because we have a constant rate of change. So there we go. For this problem, we have the coordinates of each vertex of some quadrilateral given here. And they didn't really give us the coordinates. They gave us kind of a way of figuring out the coordinates for any x and y. The key, though, they said, is that x equals y, so they're going to be the same, and they also stipulated that x is not 0, because if x and y were both 0, these would all just be the point 0, 0, which would not be very interesting. So based off of this, we want to know what kind of quadrilateral we're dealing with. So we've got square, rhombus, trapezoid, rectangle. I have a feeling we could eliminate these pretty much right off the bat. Like if something is a square, it's also a rectangle. So they're probably not going to give you something that's a square, because then do I choose square or rhombus or rectangle? Because a square is a rhombus and a rectangle. So probably can eliminate square. But beyond that, we actually need to get a visual. The tricky part here is they didn't tell you what x and y were. So one way to do this problem is to pick a value for x and therefore y and just kind of graph it out and see what it looks like. They didn't really give any other limitations on what x and y can be other than not 0. So I'm going to be lazy and just choose 1 for both of those. That should be about as easy as possible to graph it out. So plugging in 1 for x and y, my new L coordinate here is then going to be 1, 1. For M, I'm going to have 2, -1. For N, I'm going to have -2, -1. And for P, I've got -1, 1. Let me draw a very small x and y axis, and I'm just going to plot these 4 points on there and see what I've drawn. So we have 1, 1 right here, and then +2, 1 is actually down here. -2, -1 is right here, and finally, -1, 1 is right there. So connect the dots. And that is kind of the poster child for a trapezoid. So that would be choice C. For this question, all the students in Mr. Green's class are either 17 or 18 years old. There's 20 of them. And the sum of all their ages is 345 years. Based on that, we want to be able to figure out the total number of 17-year-olds in the class. Now, this is sort of a classical systems of equations sort of question. You could set up an equation that talks about the total number of students, and then you could set up an equation talking about the sum of their ages. For example, you could say like x plus y equals 20, and maybe like 17x plus 18y equals 340. And then you could solve that system and get the answer that way. But I feel like that's kind of overkill since we've got some numbers we can plug in here. So I'm just going to plug in 5 and the corresponding number of 18-year-olds to see in which of these situations I can get a sum of 345 years. So if I've got 5 17-year-olds, that means I must have, since there's 20 students, 15 18-year-olds. Let me just add those together and see what it comes out to. So on the calculator, 5 times 17 plus 15 times 18. Then this is the calculator section, so I'm going to use it. That comes out to 355. That's not too far off, but it is not 345. So we move on to the next one. So now we'll have 8 17-year-olds, and that means then we have only 12 18-year-olds. Let me see what that multiplies out to. And on my grapher, I can just go here and kind of yank my input from before and change a few things. But if you need to rewrite everything, I mean, it is what it is. So let's see here. Plugging all that in, we've got 352, still not what I'm looking for. Let me try now 12 17-year-olds and 8 18-year-olds. And back on my calculator, now I'm going to be extra fancy. And since I'm just reversing the numbers, I'm going to do 8 times 18 and 12 times 17 on here. Same thing as I have on my paper there. That comes out to 348. So we're getting closer to 345. By process of elimination, it's got to be 15. That's 15 17-year-olds and 5 18-year-olds. But if you're not sure, we can always go back and actually crunch those numbers. So we have 15 times 17 and 5 times 18. Enter, and that is 345. So there we go, choice D.